Alright guys, so today we're going to be talking about lesson 4.3, which is inverse functions and their relations. So, inverse relations are found by switching the x and y values. Note that not all functions have note that all functions have inverse relations, but all those inverse relations are not necessarily functions. So there's an easy, quick test that you can do to determine if your function will have an inverse that is also a function. So you guys all know of the vertical line test, right? The vertical line test is a test that we use in math to determine if something's a function. So the rule is if we can draw a vertical line anywhere on the function, and it only hits one point on that function, it must be a function, right? So if we look at the cubic function, we can see that it's a function, it passes the vertical line test. Now over here, what kind of function is this one under the horizontal line test? What kind of function is this, guys? Good, a quadratic. And quadratics are functions because, as you can see, they pass the vertical line test. But then we have this new thing called the horizontal line test. So the horizontal line test tells you if the inverse of your function would also be a function. So as you can see, does the cubic function pass the horizontal line test? Yeah, it does right here. What? Only once. I know it looks like right here if you drew a horizontal line. It's not actually all at the same point, it's just so it's close together. So like in a cubic function, if we were to like draw a sketch, it's really like this. So if you drew a horizontal line here, it might look like it's close to touching, but yeah, it doesn't actually touch, it just gets really close to it. So no, it does pass the horizontal line test, it just looks kind of tight in this part right here. So, as you can see, what's wrong with the quadratic function? Does it pass the horizontal line test? No, because it hits twice. So the idea here is that the inverse of a quadratic function, unless it has certain boundaries, is not a function, but the inverse of, say, a cubic function is a function. So that's how we can tell with just looking at the graph. So let's get into some inverses. So we're going to talk about the most basic type of inverse today first to start, which is basically looking at tables. So in order to find the inverse of a function using a table, all you do is you flip the x and y. So now your y's are now your x's, and your x's are now your y's. So you're just flipping around the table. That's how you find the inverse if you have a table. So I'm going to be graphing the first one in a dark forest green, and I'm going to be graphing the second one in red. So this is going to be 0, negative 1. This is 2, 0. 3, 2. And 4, 3. So it looks something like this. Now looking at relation f, is it a function? Does it pass the vertical line test? What do you guys think? Yeah. Yeah, it does. It passes. It passes the vertical line test, okay? By the vertical line test.
It passes because it crosses the x-axis, right?
No, it passes because if I drew a vertical line anywhere on here, it would only hit one point.
Okay.
So then, we want to determine before we graph it if the relation is a function. We can do that by checking the horizontal line test. Does this also, thank you, pass the horizontal line test? Yeah, so we know that our relation is a function as well. You're good. You have your packet from last time?
Yeah.
Okay, perfect.
I still this one?
Yeah, you can toss it, you're good. So we know that the relation inverse is also a function by the horizontal line test. However, we can also go ahead and graph this, right? So let's go ahead and graph our relation so that we can take a look at it. So this is at negative 1, 0. This is at 0, 2. This is, we're on 4, 3. This is 2, 3. And this is at 3, 4. So this is our inverse. So what do you notice about the relationship between the inverse, the original function, and the it's a reflection. Very good. It's a reflection across the line y equals x. You guys see that, how it's a reflection? That's always the case for an inverse. It's always going to be a reflection across the line y equals x.
Draw the reflection, right?
What?
We're not going to have to draw the reflection, right? Or
You will have to draw both of them, yep.
So we always flip the x and the y?
Yeah, if you're given a table and I want you to find the inverse, that's always how you're going to find it, is by flipping. Okay. All right, moving on. So there's also questions where we don't do graphing. We actually do it algebraically, which we're going to learn about next. So let's talk about example 2. So,
can I see that real quick?
Yeah.
Real quick. Sorry.
It's okay. So now we're looking at example 2. First thing I'm going to do, I'm actually just going to graph the relation g first. Okay, so let's just graph that in green. So that's 0, -4, 1, 2, 3, 4. That's 1, -3, 2, -1, and 3, -1. Connect them. And is this a function? Does it pass the vertical line test? Yes. But does it pass the horizontal line test? No. So the answer here is no by the horizontal line test. But we're going to actually graph it to see this for ourselves. So to find the inverse of a function via table, you're going to flip the x's and y's. So now your y's are your x's, and your x's are your y's. We're going to plot these. So this is -4, 1, 2, 3, 1, 2, 3, 4, 0, -3, 1, -1, 2, and -1, 3. Oh, hang on, I made a mistake. Just realized it. So -4, 1, 2, 3, 4, 0, -3, 1. Oh, -1, 2. There we go. That's better. Okay. So as you guys can see, they are reflections of each other. And we can also see that this would not pass the vertical line test. It's not a function, but we also knew that because of the horizontal line test. So how do you guys feel so far about using a table to find the inverse? Good with tables? Okay. So now we're going to try doing it via equation. You guys ready? All right. So we're looking at example 3. It says find the inverse of each relation and then state the inverse if the inverse of the relation is a function. So I'm going to show you guys how to do this algebraically. All right. Hang on, there's people in the waiting room. Okay, so first thing you're going to do to algebraically find an inverse is you're going to replace f of x with the letter y. First step. Next step is you're going to flip the x in the y position. So the x is now going to be where the y is, and the y is now going to be where the x is. So I just flipped x and y. Once you flipped x and y, you're now going to solve for your new y to get it by itself. Okay? So I'm going to subtract 4. I have x minus 4 is equal to -3y. I'm going to divide both sides by -3, which leaves me with y equals, and remember this is an implied 1, so this is -1/3 x plus 4/3. So I just divided both terms by the -3. You guys with me so far? So this right here is what we call our inverse, okay? No, because you're good. So it's because they're both negatives, yep. So I'm going to graph both of these to show you what they look like, okay? So negative 1/3 x plus 4/3. So if we go ahead and graph these, you guys can see the original is the one in the red, and the blue is the inverse. So see how they are inverses of each other? And if you additionally, which we do on all the graphs for your homework, if you graph the line y equals x, you see how it's a reflection across that line, the blue? So that's what an inverse looks like, okay? So moving on, let's go ahead and identify. So we call the inverse, it's just this, negative 1/3 x plus 4/3. And this is how you mathematically write the inverse. This is the notation for it. It's f with like a negative 1, it looks like an exponent of x. That's how they're saying that's the inverse of the function. And is the inverse a function? Yes or no? Yeah. So you might be thinking, how do you know? Oh, you have a question? That's what I was just going to say. So how would you know it's a function without graphing? Now, that's a good question. You have two options. If you feel comfortable with graphs only, you can use a Desmos graph to look at it. But you can also use the characteristics of the parent function. So at this stage, you guys know what basic functions look like. You know that this is a linear function. And you know that a linear function has a domain and range of all real numbers, right? So using that logic, if I draw myself a sketch of a linear function, and you kind of think of what it looks like, we know that the inverse is also going to be a function because there is nothing particular going on about it that it wouldn't be. So you kind of use your idea of how this is a function to begin with. Any function that has a domain and range of all real numbers, both the domain and range, they have to be both, we know that the inverse is going to be a function. It's when they have restrictions that it's not. For example, quadratics have a domain of all real numbers but a restricted range, right? So that's how you know that the inverse is not necessarily going to be a function. So that's what I have to say about that. Let's go ahead and try the next one to find the inverse. So the first step is to replace your y, or your f of x, with y. The next step is to now flip x and y around. Once you flip them around, you're going to solve for your new y. That gives me x plus 5 is equal to y squared. Now in this case, y squared, we have to take the what of both sides? Square root, good job. So this becomes plus or minus square root of x plus 5 is equal to the inverse y. So your inverse is plus or minus square root of x plus 5. Now this is where things get a little bit tricky for you guys, a little bit, not too bad, but this really is two different functions, right? Or equations. This is y equals square root of x plus 5, and this is y equals negative square root of x plus 5. So I want to show you what this looks like on the graph because this is a little bit weird. So if we look at our original function, what kind of function was this to begin with? Good, it was not a linear. There we go, quadratic. Okay.
This example is a real function. I didn't write it down.
Oh, yes it is, yep. So let's go ahead and look at this example. So in the blue is the original function, quadratic, okay? Does the quadratic pass the vertical line test? Yeah, but does it pass the horizontal line test? No, so we know that its inverse is not going to be a function. Now this is half of its inverse. I have to graph the other half of the inverse, which is the negative version of that. See how when I graph both pieces, it like puts them together to make the full thing, the full inverse? It's very weird. But mathematically, we don't have a way to put this as one function. It's two separate pieces, okay? But we say, you know, in the sense we say plus or minus square root of x plus 5, and that makes up the whole entire thing. But when you use graphing software, you have to put it in as two separate pieces, basically. So if we look at this as a whole entity, is this a function? No, doesn't pass the horizontal line, the vertical line test. So our answer here is no. So far so good? You guys good with this so far? Yes? No? Okay. We'll assume that you are. I have like 10 different Desmos windows open, so. Anyways, moving on. Alright, so the next one we're going to look at is, we're going to consider this function and we're going to talk about its domain and range. Because domain and range is a big theme of this chapter, because we're really getting into technicalities within math in this section. So, first thing we're looking at here is the function. Does this function have a restriction on the domain? What do you guys think? Square root functions. Can you plug anything in for x? What? No, so I'm asking, like, you know how we can't have a square root of a negative unless it's imaginary? So there's some x values that would make that negative, right? If I plugged in, like, say 1, that would make a square root of a negative. You couldn't have that. So we have a restriction on our domain, kind of like how we talked about on Monday. You guys remember? So, what can't we have in a square root? A negative, right? So to find out where the negative values start, we can set this equal to 0, right? Because right after 0 is where the negative values start. So set this equal to 0. And we're going to solve for x. So I square both sides. And I get x minus 2 is equal to 0, which means x equals 2 is where I get 0. If I plugged in 2, I would get 0 under the square root, right? Square root of 0 is 0. 0 is okay, right? We can have 0. But what happens if we pick a value of x that's smaller than 2? It becomes negative. So our domain is any value that's from 2 and greater. So 2 to positive infinity. And you can also write the domain in inequality notation, which would be x is always greater than or equal to 2. Like that. Either one is okay. So that's the domain of our function. Now the range is a little bit trickier to find, but I'm going to show you a trick that I use to find the range. So without a graph, of course you can always use a graph in that you can easily see where it stops and begins, but the easiest way to find the range is to plug in the domain value and see what you get. So if I plug in this domain value, the end point of the domain, 2 minus 2 is?
0.
Square root of 0 is? 0. So my range is from 0 to positive infinity, because the output values are never going to be, they only occur because of the input. So you can always figure it out. So your range is either from 0 to positive infinity or when y is greater than or equal to 0. I'm sorry, can you say that again? I plug in this domain value to see what I get for f of x, and that's going to be my endpoint of my range. Okay, you plug it in. You can also use a graph too, but that's just a way to do it without a graph, like a quick way. So now that we've done all that, we're going to find the inverse. So can you guys remind me the first step to finding the inverse? Yeah, we got to flip the y. Before that, we just have to replace f of x with y, right? So we replace f of x with y, and then you're right. We replace f of x with y to find the inverse, and then we flip x and y, right? So this is x now, and this is y now. Flip x and y. So now, what have I got to do? Solve for y. Square both sides to get the y out of the square root, which gives me x squared is equal to, this cancels out the square root, leaving me with y minus 2. I can get y by itself by adding 2 over, which gives me y equals x squared plus 2. Everybody good with how I got the inverse? Now the inverse we know is what kind of function? It's a quadratic, good. So this is where things get a little bit tricky, and let's look at the graph of all of this. So the first function I have is f of x equals the square root of x minus 2, right? X minus 2. So this is the first graph I have. Now, does this original graph look like a quadratic to you a little bit? It's half of it, exactly. It's half of it on its side, right? So if I graph our new inverse, our inverse function, what was our inverse again?
X squared plus 2.
Thank you. And of course, we'll always graph our line y equals x to c. So you see how this one is an inverse of this one, it's a flip of it. But what's the problem with the blue graph?
It's like full.
It's full, and this one's only half. So that's the issue with inverses, okay? The problem is sometimes, mathematically speaking, you're getting that whole entire equation. That's not the whole thing. We only want half of it. So this is where domain and range restriction comes in. So I have to restrict the domain and range of this blue graph in order to match the restriction of this. I have to basically cut it off. If I move it over here, see how it looks more like it's an inverse? So we have to cut off this part of the graph. So to do that, let's see. What's the lowest x value I want to cut this off? I want to restrict it. So I want the domain to be greater than 0. You guys see that? If I make the domain greater than 0, and I make the range greater than what? 2. That'll cut off the rest of the graph, right? Now, speaking of that, what do you notice about the domain and range of the original function?
They're like flipped.
They're flipped. Exactly. Good. Good. That's exactly what I was looking for. So, what happens is when you find the inverse of a function like this that has restrictions, your domain and range are now flipped. So we have to flip the domain and range. And you guys saw that on the graph, why we had to do that? Because we have to cut off that part of the graph that doesn't exist on our inverse. So our domain here is going to be what the range was. And our range is going to be what our domain was. Yes.
Oh, so it's always going to be flipped?
Yep. If there's a restriction at all. But even for non-restrictions, because it's both of them are all real numbers, you flip them, they're still all real numbers. So yeah, they're going to be flipped. So it's kind of a weird thing to see, but I just want to show you why. Now you can kind of see why on the graph we had to do that. Does that make sense with the graph, why we had to do it? Okay. So let's move on to an easier problem. So what kind of function is this one? And what do we know to be the case about linear functions, domain, and range? Yeah, they're both all real numbers, right? Did we finish the last problem? Okay. So, we're going to find the inverse. So to find the inverse, we replace our function with y instead of the function part, the function notation. And then we flip x and y. And then we just solve for y. So subtract 6. We get x minus 6 is equal to negative 4y. There's a 1 in front of the x, of course, so I divide by negative 4. And I get negative 1/4 x plus 3 over 2. I reduce the fraction. Everybody see how I got that? So 1 divided by negative 4 is negative 1/4. And negative 6 divided by a negative 4 becomes positive. Positive 6 over 4. Divide the top and bottom by 2 to reduce the fraction.
So you do the 1x and then you do separate?
Yeah, because basically you're dividing each term by the negative 4. So you could leave it like this, but I just write it out so it's like it's in y equals mx plus b form. So now that I have the equation, our inverse, typically you call your inverse by g inverse of x like this. You write it like this, and then you would just write what the inverse is. So now that I have my inverse, what do you think the domain of my inverse is? And the range is? Same thing. Yep. So this one was a little bit easier because they're both all real numbers. So if you graph these two lines, you'd see that they are inverses of each other. And you can always check that. On the homework, I put the line so you can see the reflection purpose as well. Okay. So I think we finished this one. Okay. Next one, we're going to talk about the composition of inverse functions. So the rule is two functions, f and g, are said to be inverses of each other if f of g is equal to x and g of f is equal to x. So basically, you guys remember how we were doing compositions on Monday? So we can compose these functions, and if the answer comes out to be x, they must be inverses of each other. Okay? if we compose them and both come out to be x, they must be inverses. So I'm going to go through this like kind of as if you haven't learned composition, just to be sure you guys got it. So I have to compose these functions. So the idea of composing is I have to take f of g of x and I have to take g of f of x. So you have to compose them like this. I think I forgot a parenthesis over here. So how do you compose a function? Well, you take the function that's on the outside, okay, the one that's on the outside, and you're going to rewrite it, but you're going to leave the x's blank. So you're either going to put parentheses there. Okay, so I just rewrote the f of x function, but I left the x blank. I removed it. And over here, you're going to do the same thing, but now you're going to do it with the g of x function. Okay? So I'm going to rewrite the g of x function, but I'm going to leave the x blank. So everybody see my setup so far? You understand it? You can see where it came from. Now, you take the inside of this, okay, and you plug it in. So g of x is what's going inside of this other function. So I'm going to replace this spot right here is going, g of x is going inside of it. Okay? And over here, they said f of x needs to go inside of it. So this right here is what's going inside. Just like that. And once you have that, you've composed them, now you need to simplify. So if I drop the parentheses here, what happens to 4 minus 4? Cancels out. So I'm just left with the square root of x, which is x squared, sorry, square root of x squared, which is just x. And that's what we want, right, if it comes out to be x. But we have to get both of them to come out to be x. So let's try this one over here. What happens to a square root if you square it? What two? This right here? It's from the original, so I have to rewrite this as like a shell without the x. So I still have to put the squared in. So this right here was the original, with what's in red was the shell of this function. So this cancels out, and I'm just left with x minus 4 plus 4. So what happens to my 4's?
Cancel.
Good. And I'm left with x for both of them. So are these functions inverses of each other? Yes. Now, just want to give you some fine print here, okay? They are inverses of each other, but that doesn't mean that they're inverses on a non-restricted domain. So basically, these are inverses, but on a restricted domain. Just like with the quadratic when we looked at, there is a restriction. So you can find that something's an inverse using this method, but it's not going to tell you about the domain restriction, so you'd have to go into further investigation about that. So I just want to put that out there and make it clear. So let's move into example 8. Can't speak. So we have to find, we don't want shapes, we have to find f of g of x, and we have to find g of f of x. So this one will be red, this one will be green. Okay? So first thing you do is you write the function that's on the outside, but you write it as empty. So you leave the x out of it. But you just write parentheses instead of the x. So the function on the outside gets written without the x in it. Everybody good with that step? Now we see what function is supposed to go inside of it. G of x is supposed to go inside f of x. So g of x is going inside, and g of x is 2 times square root of x. Over here, what's going inside g of x? F of x, which is? Good, 4x squared. Once you get to this stage, you're just going to simplify. So over here, what's 2 squared? What's square root of x squared? Very good. This comes out to be 16x. And over here, what's the square root of 4x squared? 2x, just 2x. So the squared goes away and the 4 you take as well. So this comes out to be, the answer, final answer is 4x, because you got to multiply by the 2 that was out there. So are these inverses of each other? No. Makes sense so far? Alright, so we have 2 try on your own problems. You guys want me to do them with you or you want to try them? Alright, I'll do the fraction one and then you guys can try the second one. Sound good? Alright, so let's do the second one first so that we can do this together and then you guys will try the first one on your own. So I have to compose and do f of g of x. And I have to compose and do g of f of x. So I rewrite the f of x function without the x. And I rewrite the g of x function, but leaving the x blank as well. Once you do that, you're now going to put the functions inside that they say to put inside. G of x goes inside f of x, so that's 1/2 x plus 3/2. And then over here, this is going inside. So then from here, all you really have to do is simplify each of these. So distribute 4 minus 3/4 x, good, minus 9/4. Well, so we could simplify this, right? You can combine the like terms, but do we need to? Is this going to come out to be x? No, it's not going to come out to be x, so there's really no point in continuing it, right? So we can say no, this one's not, and then this one also isn't going to come out to be x. So are these inverses of each other? No. So if you get to the point in the problem where you can see that the answer is definitely not going to come out to be x on both of them, you can stop right there. I don't recommend it on like if it looks really close, but you can clearly see this is not going to come out to be x. Yes.
So like literally it's just like plain x.
Plain x.
What if they're like the same? Like you come out.
Gotta be x. They both gotta be x. Alright, so go ahead and try the first on your own together, but not with me, on your own. And I'll put up the answer in a few.
You get the or how did you do the like x minus 8 squared to the second power? How'd you figure that out?
X minus 8 squared. How did I get this set up?
Like, how did you get to x minus 8 plus 8?
Okay, so from here to here is what you're asking.
Yeah.
Okay, so if you square a square root, it's basically like, this is like how to cancel out a square root. So if you have x squared and you take the square root of that, that cancels it out. But it also goes the other way around. So if you have the square root of x squared, it cancels it out as well. So a square cancels a square root and vice versa.
So there's, okay, I got you.
The inside is just what's left.
Okay.
Does that make sense?
Yeah.
Okay, perfect. Any other questions on this you guys want to ask me about?